So as we talk about axial loads and displacements, there's another factor that we need to consider when we're thinking about these displacements, these expansions and contractions in our members, which is this idea of thermal stress. And thermal stress just being if temperature increases, then generally something is going to expand. And if temperature decreases, then something's going to contract, which is pretty intuitive to us as we feel out in nature, right? when we're a little bit warmer, things expand, things melt, it gets colder, things freeze, bodies contract. And these displacements are measurable, right? There is actually an effect on our displacement. And we have a formula that we can use to calculate this thermal stress, this change in length due to a change in temperature. We have a linear relationship for those things. So our thermal stress, we usually represent with this equation. This is our displacement, right? Our delta, and then I use the sub T just to reference that this is thermal stress, right? It's due to temperature T. Our displacement due to the temperature is going to be alpha times delta T times the length. So this is our displacement due to the change in temperature. Then we have this alpha here. Alpha is the linear coefficient of thermal expansion. Coefficient of thermal expansion. It's a given property for a material. So much like modulus of elasticity, modulus of rigidity, Poisson ratio, all of those that we look up on our tables, we can also look up our linear coefficient of thermal expansion. It's a property of the material itself. And the units on this are going to generally be 1 over degree C or 1 over degree F. So that makes our units cancel out with our temperature units so that all we're left with is a length and a length, right? So our length units are going to match, our temperature units will all cancel out. Where our change in temperature is either going to be in degrees C or degrees F, depending on if we're in SI units or standard units, customary units, whatever system we happen to be working in. It'll just be that. We're not messing with Kelvin. We're gonna just leave him alone. We're just working in degrees C or degrees F for your change in temperature, which of course change in temperature is your final temperature minus your initial temperature. And then we have the length. And important to note on the length here, this is the initial length. So L naught, L sub O, L naught is the initial length, is what we have for this equation. So it's a fairly basic equation, plug and play equation, but we do use it in conjunction with our other displacement equation, right? We can use this in conjunction with our load displacement equation, load times length over area times modulus of elasticity, because our displacements may be affected by both things. It may be affected by both loading and some kind of change in temperature, right? This would be a very real world scenario. It's not just one constant temperature outside. If you want to build a bridge, it's going to have to withstand a lot of different temperatures. So if you've ever noticed as you've been walking over a bridge, you might see these little teeth along the bridge where two sections are coming together. Usually where the bridge is coming together at the end spans where it's connecting into normal road on the ground. And these allow for thermal expansions, right? It gives a little bit of gap so the bridge can expand and contract anytime the weather changes, right? So the teeth will get closer together when it's warmer out, and then the teeth get farther apart when it's colder out. So that way the bridge doesn't break the second it gets too hot or too cold for it to withstand. It gives it a little bit of wiggle room. So let's take a look at this in action in an example problem here. So we have this A36 steel rod that is constrained to just fit between the fixed supports when T1 equals 60 degrees Fahrenheit. So 60 degrees Fahrenheit, it is just barely snug in there. But we want to know if we raise the temperature to 120 degrees, what will the thermal stress be in the bar? thermal stress, average normal thermal stress. So for that, we know that we're going to be using our normal stress equation, right? Our normal over area. But we're going to use our thermal displacement equation that we had just talked about, so that we can find what the thermal stress is. Right? So we have our load displacement relationship and our thermal displacement relationship. So our displacement thermally is that alpha delta T times the length. Now we'll notice, since we're fixed between these two supports, we're again going to do a displacement equity, a displacement setup, right? So we know that our displacement thermally, if it's expanding thermally, say here's our bar, and it's expanding thermally, so this would be delta T, then those reaction forces are what's going to bring it back down, right? Bring this back down by loading so that it stays exactly constrained, right? The displacement has to be 0 because it's fixed between A and B. So we know displacement has to be 0. So that tells us that our displacement due to loading has to equal our displacement due to the thermal expansion. So you can write it like, dt minus dp, or just the thermal equals our load displacement, right? Because there is those reactionary forces acting back on the beam. So we have our thermal equation. We know our load equation. It's that PL over AE. And we can set those equal to each other, right? We have our alpha times delta T times length equals, equals PL over AE. So we'll notice we actually don't need these lengths, right? Our lengths are going to cancel out here. And what I need to find is the load, right? Sometimes you'll see me write this load as normal or P or F. All of those are just the loading. N for normal force, P for a general load, F for a general force. You'll see me use those interchangeably, but this P and this N are the same value. So what I'm looking for is this P value so that I can find this thermal stress in the bar. So if I solve this for P equals alpha delta T, our lengths cancel, multiplied by the area times modulus of elasticity. So now I just need to go pick out all those things that I was given, right? So let's start with our alpha, our linear coefficient of thermal expansion, which isn't given to us in the problem statement, but again, we're told that this is a bar made of A36 steel. And A36 steel we have in our handy dandy table. So we can go into our table and look up this linear coefficient of thermal expansion. And, we'll also pull the modulus of elasticity while we're there, because we're there. Might as well grab everything. So we're not working in SI units because we were working in Fahrenheit. So we're in our US customary units, and we have A36 steel here in the middle, top of our white bar. At the very end here, our coefficient of thermal expansion alpha. Note that it says 10 to the negative 6th. So whatever this value is multiplied by 10 to the negative 6th. So it is 6.6 times 10 to the negative 6 per degrees Fahrenheit. I didn't do the thing I said I was going to do. I didn't pull modulus of elasticity. It's 29 times 10 to the third KSI. Okay, let's write both of those down. All right, so from our table, this was 6.6 times 10 to the negative 6 per degrees Fahrenheit. And our modulus of elasticity is 29 1,000, because 29 times 10 to the third, KSI. So we can pop those puppies right into our equation here. So we've got 6.6 times 10 to the negative 6. Then our delta T term, our delta T, our initial temperature is 60 degrees Fahrenheit. Our final temperature is 120. So 120 minus 60. 120 minus 60. Or you can just write 60 in there. Our area is our cross-sectional area, which they gave us right below the diagram. This cross-section is a square cross-section of 1/2 inch by 1/2 inch. So we'll multiply by 0.5 times 0.5. And then really I can just, if I move this, I can just say multiply by 29,000 KSI. Right, I can just bring this guy over. Let's do that. Oop. Oh no, my scribbles are in the way. All right, there he is now. So this is my full equation, so I can punch all that into my calculator, and it gives me 2.87 kips. 2.87 kips. So that's my loading. So once I have that, all I need to do is plug it into my stress equation, where I say stress is 2.87 kips over that cross-sectional area, which was 0.5 times 0.5 since it was a square, which we could have gone ahead and done this all in one step and just canceled out the areas here, but that's okay. We're here now. And I punch that in the calculator and get a value of 11.48 KSI, kips per square inch. So that would be the thermal stress, right? So this is thermal displacement that we've been working with, and we use that, this is thermal displacement, and we use that to calculate our thermal stress. The stress that the bar is feeling because of that expansion, because it's trapped between those two fixed locations. A fairly simple example, but can be used in more complicated examples. So let's take a look at another one. In this example, we have a rigid beam in yellow here that is fixed to the top of these 3 posts. The 2 outer posts are made of steel, and this inner post is made of aluminum. As A992 steel and 2014 T6 aluminum, initially at 20 degrees Celsius. Then we add in a distributed load and raise the temperature to 80 degrees Celsius, and we want to know what the force is supported by each post. So once it's subjected to both the loading and the temperature change, we want to know what the load will be for each post. So the first thing that we probably want to do is make a free body diagram. That's a great instinct to have. If that's where you say we need to go, that's right. We need to go with a free body diagram. They're always going to help you. Always, always. Diagrams are always helpful. So let's just take a look at that rigid bar there. So for our rigid bar, keep him in yellow, we have that distributed loading on top over that 600 millimeter span, the full span of that guy. And then we have those 3 posts, and they're equally spaced. It says each is at the 300 millimeter mark. So we're going to assume they're equally spaced there, where I have my distributed load. If I work it out, I get 150 kilonewtons per meter times the 0.6 meters that it travels over. So that's 90 kilonewtons. And then I have the load from the steel, load from the aluminum, load from the other steel beam. And what I can do with my free body diagram is set up my equilibrium equations, right? So I can do my summation of y forces, but we notice that our diagram is exactly symmetrical. right? If I take a moment about the aluminum here, about this point here, or to take a moment for this diagram, I would see that my distributed load cancels with my aluminum, which means that my steel loading has to exactly cancel out, right? The loading of each steel post is going to be exactly the same. So that means my load here and my load here are going to be the same. I don't actually need separate variables for each of them, right? Just taking a moment about point, or a moment about beam, the aluminum beam, is going to show you that we can treat those both as equal. This is a perfectly symmetrical diagram, so we can make that assumption, which will make our calculations a little bit easier, because now we'll only have 2 unknowns instead of 3. If I do my summation, y equals 0, I'll get 2 of my load for the steel beams, plus whatever the load is for my aluminum beam, minus the 90 kilonewtons, which I'm going to convert to 90,000 so I don't forget to do it later, and just keep everything in uniform units. So now I only have 2 variables that I'm looking for, right? Two unknowns. So I need one more equation so that I can figure these out. And we're going to go back to our load compatibility, right? Our load displacement equations. Create a compatibility equation for this. So when we look at this, if we want to create a compatibility equations to give us our second equation here, we have to think about what the load is doing, right? So it's a rigid beam that's perfectly symmetrical, perfectly loaded. So any displacement that occurs is going to occur with the whole bar moving up or down, right? The displacement will be entirely in one direction. So it could move down, could move up. Let's assume it moves down, maybe, right? This would be the displacement of the full bar, right? It's not going to be angled or tilted or in any way. They are fixed to the top of this beam. Everything is symmetrical, which means that my displacement of my steel beams here have to be exactly the same as my displacement of my aluminum beam, right? However much the aluminum beam moves, or the aluminum column, I guess, aluminum post moves up or down, my steel beams are going to have to move up and down the exact same because they're fixed, going to remain totally straight. Because if my steel beams both move up, that's going to mean that my aluminum is being affected in the exact same way, right? It's being affected in the middle here because it's fixed. So my aluminum displacement has to equal my steel displacement. It doesn't really matter what those displacements are, like to calculate a number for what that displacement actually is. What really matters is setting up those equations so we can find these loads, because that's what they ask for in the question. They ask us to find the force in each post. So really, we don't need a firm number for these. We just need some equations with our load relationships in them. So for our steel beam and our aluminum beam, remember we're being subjected both to that distributed load and to the thermal stress. So when we calculate the displacement for each of these, we're going to have to include both equations. So our delta aluminum is going to be the thermal expansion due to the aluminum plus our load displacement equation, right? And that's going to be the same for steel, just with different numbers put in there. Right, so if we do this for aluminum first, well, we do them at the same time. I don't know that it matters if you do them at the same time. We could do both, right? We could set up alpha aluminum, delta T length plus load length over area, which is different for aluminum. Modulus of elasticity for aluminum. Oh, this is load AL. Length AL equals thermal coefficient of expansion of steel, delta T times the length, plus load steel, length steel, over area steel, modulus of elasticity of steel. So if we do set these all up in one equation, we can actually cancel the length because our posts are exactly the same height. They're all at 250 millimeters. So it doesn't actually matter what the length of these guys are. We can cancel out all of the lengths. It's the same for the aluminum and the steel. But we do need to go ahead and pull a couple of values for ourselves so we can get this relationship between our load aluminum and load steel. We're going to need our modulus of elasticity and our thermal expansion coefficient. So for aluminum, it's a 2014 T6 aluminum. We'll pull up our table real quick. And we're working in what units? These are the SI units. So we'll come back up to our SI table. And let's see our materials. Oh, good. It's our very first one. Aluminum, 2014 T6 aluminum. Thermal coefficient expansion is 23 times 10 to the negative 6. And modulus of elasticity is 73.1 gigapascals. All right, so 23 and 73.1. This is 23 times 10 to the negative 6. And our other, well, I'll just type all this other stuff in too. Delta T is 80 degrees minus 20 degrees Celsius. Gives us 60 degrees Celsius. So our units for these guys will cancel. Got rid of the length. So we just have P, AL. Now I do think I missed a sign change in here. Ah, yes. See, I've assumed that all of my bars are in compression. This needs to be negative. All right, and then my area of AL, it gives me a diameter of 60 millimeters. Diameter of 60 millimeters, so that's pi over 4 times 0.06 squared. Times modulus of elasticity, we said was 73.1 gigapascals. Giga is 10 to the 9th. Ooh, my goodness, that's just one side of the equation. Now we'll do our steel side of the equation. Maybe I'll do that in a different color just to liven things up. Let's do steel gray, nice and lively. We'll need to pull our thermal coefficient of thermal expansion, and modulus of elasticity for A992 steel. A992 steel. Open up our table. I'm going to take a look down here. It's right under our favorite guy, A36. Our second one down. So his modulus of elasticity is 200 gigapascals. His coefficient of thermal expansion is 12 times 10 to the negative 6 degrees C. All right, so that's our 12 times 10 to the negative 6 times delta T is again the same 60 degrees minus, right? I had a sign change in here because this is not plus. these are minuses in compression. Minus our load steel, pi over 4 times, what's the area of our steel beam? 40 millimeters. So 0.04 meters squared. I like to do the conversions just on the fly so I can have everything in the right units. It would maybe be a good idea to convert everything up top first and then plug everything in, but up to you. what do we say? We said 200 gigapascals. So 200 times 10 to the 9th pascals for our modulus of elasticity of steel. So that is our equation. That's our equation setup, where we can take our original equation here, maybe solve for P aluminum. Our aluminum load would be 90,000 minus 2 P steel. We could plug this into our, plug it in here. Now we have everything in terms of P steel, and we can find the load on that steel. So I'm not going to go through all the algebra of this. You can put this into an equation solver. You can do the algebra. I believe in you. And we're going to get a value for P aluminum of 123 kilonewtons. And for the load steel of negative 16.4 kilonewtons. Right, so what does that mean practically? Right, that means that our steel posts are in tension. Right, the way I had drawn them, I had assumed everything was in compression, but our steel posts are actually going to be in tension. Right, they're going to be pulled up by that fixed bar. That fixed bar is pulling up on them. And our aluminum is being compressed. Our aluminum is being compressed down. And this is only because I had assigned the loads wrong. I had assumed all of these were acting in compression, when actually our steel is in tension and our aluminum is in compression. That's all those signage mean. It's okay if your signs turned out to be the opposite of that. It just means you had assumed differently a free body diagram than I did. But this is how we would use our thermal displacement in conjunction with our loads at the same time, so that we can accurately calculate our displacement. Right? Our thermal displacements, our temperature does have an impact that we need to take into account.